Hello and welcome to our third video on convective turbulence. In this video, we're going to look at the causes of instability in the atmosphere. Generally speaking, the instability in the atmosphere results from the temperature profiles of the parcel and also the temperature profile of the atmosphere or the environmental lapse rate. This is what meteorologists look at when they think about the atmosphere, when they start looking or start thinking about the lowest layers of the atmosphere. We think that the lowest, very few hundred feet above the ground, the temperature lapse rate decreases very rapidly. Now this is the environmental lapse rate. In other words, if you sent up a weather balloon, you would measure a very rapid decrease in temperature in the lowest few 100 feet. That makes sense because the surface or the air is heated from the surface below. So if the ground heats up quite a bit, the air in contact with the ground will be very warm. But as you rise a few hundred feet above the ground, the temperature will decrease very rapidly as you get farther away from the surface. Above that, there is an adiabatic layer. This is where the parcels of air rise adiabatically. Typically, that's a result of mixing of the atmosphere. And then above that, a few thousand feet into the atmosphere, you have the free atmosphere. So that's all pretty technical. You don't need to memorize those terms. Instead, what we're going to do is we're going to simplify it. And we're going to add, or we're going to combine the superadiabatic and the adiabatic layer, and we're going to call that the convective or mixed layer. Convective for, convective mixing or convective rising of parcels of air, and mixing because as air rises, you have to have compensating motions, and air also sinks in that region. So the air becomes kind of mixed. It's all mixed up. And pretty soon the entire lapse rate becomes dry adiabatic as the day progresses and the atmosphere heats from below. At the very top of this mixed layer or this convective layer is a temperature inversion. Remember we said that thermals rise until the temperature inside the parcel equals the temperature outside. And the reason the temperature outside reaches the parcel temperature is because there is usually a very weak inversion at the top of the boundary layer or this mixed layer or convective turbulence layer. And thermals will rise up to that and they bubble up maybe a few hundred feet above that, and then they stop and come back down. You can see this temperature inversion, this capping inversion, very well on soundings. And we'll look at that when we look at a case study. We'll look at some temperature inversions that prevent thermals from rising. But typically that is the top of the mixed layer. And if you can fly above that, you'll get a nice smooth ride because it's stable above that.
This can be seen in a thermodynamic diagram. In particular, we have the skew-T log P diagram here. And this is from a particular day, a nice warm summer day in 2020. The temperature profile is indicated by the red line, the dew point profile in the atmosphere, the green line. And as we discussed before, the dashed red line represents the dry adiabatic lapse rate, the rate at which the parcel rises and cools in the atmosphere. And as long as the parcel temperature is warmer than the environmental temperature, or for that matter, the same temperature as the environmental temperature, just slightly warmer, it'll continue to rise through the atmosphere. That happens up to a point just around or just below the inversion. You can see the capping inversion shows up really well on this sounding. And that inversion indicates, of course, where the temperature increases with height. Above that point or just slightly below and then up through the atmosphere, as the parcel rises, it'll be colder than the environment, and as a result, it won't want to rise unless it's forced to rise. I've taken away the warmer and colder than the environment shading, and in this case, you can see where the capping inversion is. And also I drew some arrows to indicate that that is typically the height at which thermals rise. Even though the temperature of the parcel may be slightly colder or a little bit colder than the environment, and it'll want to sink, it may have some momentum, and it keeps rising typically to the capping inversion. So the capping inversion actually acts as a lid for the layer of convective turbulence. Above that, you get a smooth ride. Below that, it can be pretty choppy. And on this particular day, you can see that the capping inversion occurs slightly above 700 millibars. And as you remember, 700 millibars is about 10,000 feet. So on this day, to get a smooth ride, you'd have to climb up above 10,000, maybe to about 11 or so, to get a smooth ride. This is why it's really nice to look at soundings when you go flying. They give you an idea of the state of the atmosphere and where you're going to get a smooth ride and where you'll get a turbulent ride.
So there are two ways which instability can cause convective turbulence. One we already discussed, and that is surface heating. The other one, not so much, and that's with cold air advection. With solar heating, as you would guess, the sun heats the ground. Radiation, solar radiation is absorbed by the ground. That raises the temperature of the ground, and the air in touching the ground warms up also. Those thermals start to rise. So we're going to look at the variables and the characteristics of the solar heating. Variables, things that determine how much solar heating occurs, of course, is the time of year, the time of day, the terrain, and also the wind. As far as the time of year, summer typically you have the longest days and the strongest solar radiation, so you get the worst convective turbulence, worst and strongest convective turbulence. Time of day, of course, is in the afternoon. At night there's no sun, but at night in the afternoon you have lots of heating and lots of thermals. Also, the terrain plays a huge factor in determining how much convective turbulence occurs. Think about flying over a body of water. The sun doesn't really heat the water all that much because the water has very high specific heat, meaning that it takes a lot of energy to raise the temperature. Whereas rock probably has a very low specific heat. So if the terrain is very rocky, mountainous terrain tends to have very low specific heat and usually the worst type of convective turbulence. And then also when the winds are rather light, thermals are allowed to rise straight up. If the winds are very strong, then the thermals kind of get all mixed up and chopped up and they never produce convective turbulence. So the type of turbulence, convective turbulence that you get with solar heating is usually light to moderate. It's not usually severe turbulence, but if you're flying a V-tail Bonanza that has an airplane that has not a lot of directional stability and you're sitting in the back, you can get sick pretty easily in convective turbulence. The depth of the convective turbulence, of course, depends upon the temperature profile of the atmosphere, but usually across the central plains of the United States, usually you'll see the height of the convective or mixed layer goes up to about 5,000 feet. But however, over mountainous terrain like Colorado or Arizona, you'll see the layer of convective turbulence go up to 14,000, 15,000 feet because you're starting at a much higher elevation already. The other cause of instability is cold air advection. Cold air advection is where cold air moves over a region, and if the ground is warm, then you have an unstable situation where you have a colder atmosphere and much warmer ground. The air in contact with the ground will warm up, causes bubbles of air or thermals to rise through that cold air, and usually this type of thermal or convective turbulence is usually pretty significant. Where will you find it? Usually behind a cold front. In the high pressure, nice high pressure dome behind a cold front, usually the air is also pretty cold, and also the winds are usually pretty light when you get in towards the center of the high. So the times of year that you'll find the cold air advection, in other words, when do you find these cold fronts moving out of Canada? Usually when the ground is already warm, still warm, such as in the spring and also in the fall. And with cold air moving out from Canada produces regions, large regions of convective turbulence. And of course, you need light winds. If the winds were stronger, then you'd have more of a mechanical turbulence than convective turbulence. That's all for this video. In the next video, we're going to talk about how to identify thermals and thermal patterns.